Hello, this is Zachary May with the National Weather Service office in Memphis, Tennessee, and in this presentation we will discuss the El Niño Southern Oscillation, or ENSO. ENSO has worldwide impacts on climate, impacts which are realized by our local climate around the Mid-South. It is the goal of this presentation to acquaint you with ENSO, what it is, and how it affects our climate. We will begin with an overview of what ENSO is, including the atmospheric causes behind it, and worldwide responses to climate regimes typically noticed during an El Niño or La Niña event. Next, we will discuss how ENSO is measured. This is important to understand because we must be able to measure ENSO in order to determine the type, either El Niño or La Niña, and magnitude of the event. In doing this, we will also share the criteria for declaring an ENSO event. A local climate study of the effects of El Niño, La Niña, and ENSO neutral events has been conducted for the Mid-South using data from Memphis International Airport, and these findings will be presented in order to understand the effects of ENSO on our climate in the Mid-South. Finally, an introduction to the Climate Prediction Center will be offered, which will educate you on a plethora of climate resources available online. Before we dive into the specifics of ENSO, let's first take a look at the history behind the oscillation. ENSO was first noted by residents of coastal Peru, which is home to one of the world's largest fisheries. These fisheries noticed that every few years, warmer sea surface temperatures were causing increased amounts of precipitation, which would as a result hinder the success of the fishery. This warmer than normal water off of the South American coast extended west towards the dateline across the equatorial Pacific Ocean. Because this typically occurred in late December around the Christmas holiday, the warmer than normal sea surface conditions were named El Niño, or the Christ Child. Conversely, La Niña is just the opposite and refers to cooler than normal sea surface temperatures in the eastern Pacific, extending west towards the dateline across the equatorial Pacific. El Niño and La Niña refer more to sea surface temperatures across the equatorial Pacific, but these are accompanied by a change in the atmospheric circulation known as the Southern Oscillation, and thus the name El Niño Southern Oscillation, or ENSO. The Southern Oscillation is measured as the sea level pressure difference between Tahiti and Darwin, Australia. In meteorology, differences in pressure drive winds, and thus the greater the difference in sea level pressure between these locations, the faster the wind. As illustrated by the image in the lower right, the pressure differences between the eastern and western Pacific drives the Walker circulation. The Walker circulation goes as such. Trade winds blow from east to west across the Pacific, ascend in the western Pacific, and then flow back at high altitudes before descending to the surface in the eastern Pacific. As the winds blow across the ocean surface, they transport the warm waters near the surface to the western Pacific, where the ascending branch of the Walker circulation aids in convection, or the rising of warm moist air upward into the atmosphere. This creates a lot of rain in the western Pacific, while the movement of the warm water to the west across the Pacific allows for upwelling of cooler ocean water to near the surface in the eastern Pacific. This is illustrated by the image on the left, which represents an ENSO neutral phase where neither an El Niño or La Niña event is occurring. So putting our sea surface temperatures together with our Walker circulation, or Southern Oscillation, we get the El Niño Southern Oscillation. This is because there is a positive feedback between the atmosphere and the ocean. This means that a decrease or even reversal in the trade winds will allow warmer water to remain in the eastern Pacific, creating El Niño conditions, as the lack of wind will allow the warmer water to remain off the coast of South America, as little upwelling of cooler ocean water will occur. Previously, I stated that a difference in pressure drives the wind, but this is also true of temperatures, and the larger the temperature difference, the faster the wind, as sea surface temperatures do act to modify the near-surface atmosphere. Thus, if the sea surface temperatures are uniformly warm across the equatorial Pacific, the trade winds will be lessened as the temperature gradient is reduced, thus the positive feedback between the atmosphere and ocean. This is exactly what occurs during an El Niño event, where warmer than normal sea surface temperatures are observed in the eastern Pacific, as illustrated on the left side of the image. On the other hand, if trade wind strength is increased, more upwelling will occur in the eastern Pacific and more cool water will be transported across the Pacific, while more warm water will be pulled in the western Pacific. This essentially creates a large difference in sea surface temperatures between the eastern and western Pacific, thus further increasing the trade winds and driving the cooler waters further across the Pacific. This is what happens during a La Niña event, illustrated on the right side of the image. Ultimately, the changes in sea surface temperatures affect the distribution of tropical rainfall and atmospheric circulation features, primarily the jet stream. The image on the far right illustrates normal conditions across the Pacific, or ENSO neutral conditions, which we saw earlier. In this scenario, the Walker circulation moves warmer water across the Pacific where it pools in the western Pacific. We use December through February conditions for these illustrations, as the effects of ENSO are most prominent during the cool season in the northern hemisphere, as this is when the jet stream, which is altered by ENSO, is the strongest. The center image illustrates La Niña conditions, and we can see that the trade winds are stronger in this scenario. Thus, the cooler waters are being carried further across the Pacific. The growing sea surface temperature gradient can be seen, and this is acting to drive the winds even faster. Going back to the positive feedback cycle we just discussed. Finally, the image on the left illustrates El Niño conditions where we have uniformly warm water across the Pacific, greatly decreasing or even reversing the trade winds. This scenario creates a lot of convection in the central Pacific, which acts even more to alter the jet stream. Think of this convection as a boulder placed in the center of a stream. The flow of the water, or wind in this case, will be altered and forced around the boulder. Essentially, this is how ENSO has an effect on worldwide climate regimes. So what are these effects that ENSO can have on worldwide climate regimes? The image on the left shows the typical La Niña effects during the cool season from December to February. Notice the large area of dry and cool conditions across the Pacific due to the cooler ocean temperatures in that area. Notice the dry and warm conditions across the southern U.S., while cool and wet conditions dominate in the Pacific Northwest, with cooler than normal conditions over parts of western Canada and southern Alaska. Taking a look at the El Niño effects in the image on the right, it can be noted that these effects are just about the opposite of the La Niña effects. Conditions over the equatorial Pacific are wet and warm due to the warmer ocean temperatures and resulting convection and rainfall in the area. Now that we have established an understanding of what ENSO is, we will now take a look at how it is measured. Sea surface temperatures are affected by ENSO and therefore are used as a proxy to measure ENSO. This is done by observing the anomalies or differences from normal conditions. We accomplish this using the Oceanic Niño Index, or ONI, which is a 3-month average of the anomalies of sea surface temperatures in a specified region of the Pacific, illustrated by the box in the image. Sea surface temperature differences within the Niño 3.4 region are averaged out over 3 months, and this departure from normal becomes the ONI value. Since warmer than normal sea surface temperatures lead to an El Niño event, positive ONI values of 0.5 or greater signify El Niño. Conversely, cooler than normal sea surface temperatures comprise a La Niña event, and thus negative ONI values of negative 0.5 or less signify La Niña. The criteria for declaring either an El Niño or La Niña event are that the ONI value remains in category for either El Niño or La Niña for 5 consecutive overlapping 3-month periods. For instance, if the first 3-month period for an ONI value of 0.5 was August, September, October, the value would have to hold at or above 0.5 for the following 4 3-month periods: September, October, November, October, November, December, November, December, January, and December, January, February, in order to be classified as an El Niño event. A local climate study was performed in order to determine the effects of ENSO on the climate of the Mid-South. To do this, ONI values were compared to departures from normal for the 3-month period averages of temperature and precipitation in order to identify relationships between the two, such as negative departures when the ONI is positive. All data in the study were from Memphis International Airport, and events were categorized either El Niño or La Niña and then analyzed by strength, weak, moderate, or strong. 40 events total were studied, and these events occurred between 1950 and 2013. 15 of the 40 were El Niño events, another 15 were La Niña events, and the final 10 were periods where the ONI value was neutral or when no El Niño or La Niña was ongoing. Within these 10 neutral events, 5 were when transitioning from El Niño to La Niña, and the other 5 were from La Niña to El Niño. We will now take a look at the results. We begin with the strong ENSO events, these being either El Niño events with maximum ONI values greater than 1.4 or La Niña events with minimum ONI values less than 1.4. Notice that the table on the left is the temperature data, while the table on the right is precipitation data. The far left column identifies the 3-month periods, while the El Niño and La Niña columns contain average departure from normal values and tell us whether temperature or precipitation values were above or below normal for the period indicated by the far left column. The values in blue in the temperature table indicate below or cooler than normal temperatures, while red values in this table will indicate temperatures that are above or warmer than normal. Black values in both tables will indicate values that fall at exactly normal. Green values in the precipitation table will indicate 3-month periods with above normal precipitation amounts, while values in red indicate below normal precipitation. The correlation values on both tables will allow us to see if there are any relationships between the ONI values and departures from normal. Values closer to 1 or -1 indicate a stronger relationship, while values near 0 indicate very little relationship. Beginning with the 5 strong El Niño events studied, we can see that all periods during an El Niño event had below normal values, indicating that strong El Niño events tend to have a cooling effect on our climate. The correlation is near 0, showing there is little relationship between ONI values and departures from normal. The precipitation values are predominantly above normal, indicating that strong El Niño events can lead to above normal precipitation amounts around the region. The correlation is not that great between ONI values and precipitation departures from normal, which can be expected due to the variability found in precipitation totals. For the 5 strong La Niña events studied, the average temperature departures from normal were mostly above normal, meaning warmer temperatures were most likely during a strong La Niña event. This is not the case, however, for the March, April, May through June, July, August periods, when temperatures are either near or slightly below normal. This is likely due to the fact that the effects of ENSO events are strongest during the cool season, since the alteration of the jet stream is greatest at this time. There is a moderate negative correlation between the ONI values and temperatures, indicating that temperatures are most likely to rise as the ONI value decreases during a strong La Niña event. Whereas strong El Niño events have a cooling effect on our climate, strong La Niñas appear to have a slight warming effect. As for precipitation during strong La Niña events, the first half of the year has the best chance of being wetter than normal, while the second half of the year has a better chance of being drier than normal. This correlation is somewhat moderate between ONI values and precipitation, meaning the stronger the La Niña event, the better odds of more precipitation than normal. The moderate ENSO events were those with ONI values between 1 and 1.5 for El Niño and -1 and -1.5 for La Niña. Notice with the moderate El Niño events that, while most periods still have departures below normal, there are now 2 periods that are either at or just above normal. However, the largest departure of any El Niño event is found in the moderate type, with January, February, March having an average departure of 1.7 degrees below normal. The correlation between the moderate departures and ONI values is the best of any of the El Niño events, meaning the strongest relationship between the ONI values and the temperatures is during moderate events. This negative correlation suggests that as the El Niño becomes more moderate, temperatures are more likely to be below normal. On the precipitation table, there are more periods with below normal precipitation totals, with the fall months having above normal totals. The correlation for the precipitation values, like the temperature correlation, is the strongest of all the El Niño events. For the moderate La Niña events, temperatures tend to be above normal in the cooler months, and again, this is the time when we expect the maximum impact from ENSO events, as the jet stream is at its strongest during these months. In fact, the warmest departure from normal, 1.9 degrees, is recorded in October, November, December, and December, January, February during the moderate La Niña events, and this departure is the warmest of all La Niña events studied. The spring and summer months have below normal temperatures, while the correlation suggests that as La Niña events become more moderate, the temperatures increase. Quite a bit of variability in the precipitation, with about half the periods becoming above normal and the other half below. Weak ENSO events have ONI values ranging from 0.5 to 1.0 or negative 0.5 to negative 1.0. Looking at temperatures for weak El Niño events, we can see the temperatures are still below normal for the cool months, but we now have more warmer months with near or above normal departures, specifically May, June, July, which has a 2.0 degree departure above its normal. The correlation is not too strong, but still suggests that temperatures cool as the El Niño event strengthens. Most periods have below normal departures for precipitation, but there is still a discontinuity between periods, as well as a low correlation between precipitation totals and the ONI values. We notice more warmer than normal temperatures with strong La Niña events, a few less than with moderate La Niña events, and now there is only one period with a departure above normal with the weak La Niña events. Out of the 5 weak events studied, none were ongoing during the March, April, May period and thus could not be considered. The summer departures are some of the coolest of all ENSO events studied, with the July, August, September period having the largest departure below normal of the entire study. However, the correlation is low, indicating little relationship between temperatures and ONI values. Meanwhile, as with the weak El Niño precipitation totals, the weak La Niña totals have little continuity and little correlation. The final step of the local study was to average the departures for all 15 El Niño events and the same for all 15 La Niña events. The departures were also averaged for the neutral events and are included here. First, noticing temperatures for the El Niño events, we can see an overall cooling effect, with the exception of the May, June, July period, which has an above normal or warmer than normal departure. The January, February, March period has the greatest departure. We can infer from this that during an El Niño event, odds are best that temperatures will be cooler than normal, although by only a degree on average outside of the cool season. There is fairly strong negative correlation with the El Niño temperatures to the ONI values, meaning that as an El Niño event becomes stronger, the temperatures become cooler. The La Niña event temperatures have the best odds of being above normal during the cool season, with the average departures above normal all being less than 1 degree. The largest departure among the La Niña event temperatures is actually during the summer months, when the June, July, August period experiences an average 1.4 degree departure below normal. Like the El Niño event temperatures, the La Niña event temperatures are also well correlated to ONI values. This means that as the La Niña event strengthens, the temperatures are likely to warm. This proves that ENSO events are strongest during the cool season, as this is when La Niña event temperatures are above normal, which the negative correlation suggests should be with an increasing ONI value. There is not much continuity with temperatures with the neutral events, so we can make very few inferences about what happens during these periods, other than that cool seasons are somewhat warmer than normal on average. There's still not too much to say with precipitation data. As we will see on the next slide, there is just too much variability and too little continuity from period to period with precipitation to make many conclusions. Notice the lower correlations also tell us that there is little relationship between the average ONI values and the average precipitation totals. One interesting thing to note about the precipitation data would be the below normal totals early in the year, with above normal totals later in the year. This graphic shows plotted ONI values, the blue and red bars, where the red bars indicate El Niño and the blue bars indicate La Niña, and the 3-month average precipitation departures from normal on the black line. The horizontal red and blue lines show where El Niño and La Niña thresholds are met, respectively. Notice here how frequently the precipitation totals change. There are few instances where the ONI values and precipitation totals seem to be well correlated, other than the 1998 to 2001 La Niña event, where the precipitation totals were below normal throughout the event. During the 2009 El Niño event, precipitation totals are above normal, but they fall below normal midway through. The important thing to take away from this graphic is the variability in the precipitation totals. This makes it very difficult to make any inferences about how wet or dry it may be during an El Niño or La Niña event. This graphic shows the same information as the last, but this time the black line shows a 3-month average of temperature departures from normal. Notice there are far fewer changes with the temperatures, which shows far less variability than the precipitation values. By looking at departure from normal, we can remove most of the seasonal variability, so this allows us to see how ENSO can affect the temperatures, and we can see there is more correlation with the temperatures than there was with the precipitation values. First, notice how temperatures were below normal for the most part during the strong 1997 to 1998 El Niño event, while they were above normal during the 1998 to 2001 La Niña event. Of course, this is not always the case, as we can see below normal temperatures during El Niño events from 2002 to 2005, but it does seem to suggest that the stronger an El Niño event or La Niña event is, temperatures are likely to respond above normal during a La Niña and below normal during El Niño. To summarize all that has just been presented, during any El Niño event, the chances are increased for cooler than normal temperatures, and this is amplified in the cooler season when the effects of the altered jet stream are stronger. Further, moderate El Niño events have the strongest correlation between temperatures and the ONI values, suggesting that as an event becomes more moderate, the cooler the temperatures become. Stronger El Niño events provide enhanced odds of experiencing cooler than normal temperatures, and if the event is strong enough and lasts long enough, this can be felt year-round. While there is quite a bit of variability in the precipitation totals, the data suggest a better chance of more periods having above normal precipitation totals during strong El Niño events. Warmer than normal temperature odds are increased during the cool season of a La Niña event, while cooler than normal temperature odds are increased in the warm season. Like El Niño events, the strongest correlation between temperatures and ONI values are also found in moderate La Niña events. Strong La Niña events provide enhanced odds of experiencing warmer than normal temperatures. Finally, relationships between ENSO events and precipitation totals are difficult to define as there is more variability and less correlation within the data. However, the best relationship between the two is found during moderate events. Perhaps the most important thing to take away from this presentation is that there are other factors affecting our climate in addition to ENSO, these being other atmospheric oscillations that can either work with or against ENSO. Therefore, this local climate study on ENSO cannot be taken as a prediction for any given event, but rather a look at what has occurred in the past during ENSO events. The Climate Prediction Center is a great resource for long-term climate forecast information. Here, you will find monthly temperature and precipitation outlooks for up to a year in advance. In addition, there are also outlooks provided for ENSO and the other atmospheric oscillations that can affect our climate, as well as drought outlooks. You can visit their website at www.cpc.ncep.noaa.gov. Thank you for watching this presentation on the El Niño Southern Oscillation. For more information about our local weather or climate, please visit our website at weather.gov/Memphis. Also, be sure to like us on Facebook and follow us on Twitter.